Alright, hello guys, welcome to lesson 10.1, acid and base reactions. There's two really long examples in this lesson, and so I'm going to take one example and then I'll probably make another video for the second example so it's not too long. So for example number 1, it says to consider the reaction between acetic acid and sodium hydroxide. So the key words there are acetic acid and sodium hydroxide. So we know that acetic acid is just vinegar, which is HC2H3O2. And it is a weak acid, so it's not going to split apart. And sodium hydroxide is NaOH. That's a strong acid, so that one is going to be aqueous. So that one will split apart. Right, so we're writing the balanced net ionic equation. It's a double replacement, so H and OH come together to make water. And then sodium and acetate come together to make sodium acetate. So C2H3O2. That is an oxygen right there. All right, and then this one is aqueous. It splits apart based on our solubility rules, group 1, and then acetates. All right, so splitting these apart, we know that sodium is the only one that cancels out because when you split it apart, Na plus and OH minus, and on the other side we have Na plus and C2H3O2 minus. Acetic acid and water do not split apart. So rewriting this equation, we are going to have acetic acid, HC2H3O2, hydroxide, which is OH minus, water, and acetate. And so that is our overall balanced net ionic equation, right? We have one acetate on both sides, and we have two hydrogens and one oxygen for the water. So this one is balanced right here. All right, scrolling down to the next one. For B, it says if 40 milliliters of 0.1 acetic acid is combined with 30 milliliters of 0.1 sodium hydroxide, calculate the moles of each substance, assuming that the reaction goes to completion. So let's go ahead and do that. All right, so to start off with 40 milliliters of 0.1 acetic acid, we're going to calculate the moles of each of those, right? So let's calculate the moles. So the moles of acetic acid, I'm going to shorthand acetic acid to HA, so that way I don't have to write it out each and every single time. And so we have 0.0400 liters. That's our volume, so I converted 40 milliliters to liters, times 0.100 molarity, right? And molarity is moles over liters, so multiply liters and molarity, the liters will cancel out and you're left with moles. And so when you multiply those two together, you end up with 0.004 moles. So 0.004. If you're going to the correct amount of sig figs, 0 moles. All right, and then for sodium hydroxide, we have 30 milliliters times 0.1 as well. So for a hydroxide, we don't care about the sodium, remember, because it cancels out, so we just really care about hydroxide. So we have 0.0300 liters, and we have 0.100 molarity. Again, liters cancel out, we're left with moles. And so for this one, it's going to be 0.003. And if we're going to the correct amount of sig figs, it would be 0 moles. All right. The next step for this is we need to set up an ice table based on this, but the ice table for this is going to be just moles, not molarity. So our ice table will be moles. And so I'm going to rewrite our equation that we had up above just to understand where we're getting that from. Let me change this pencil to a darker one. So we have HC2H3O2 plus we had OH minus, and then it yielded C2H3O2 minus, that was acetate and water. And so our ice table for this one is going to be in moles instead of molarity, so just keep that in mind. For this one right here, our initial of acetic acid is coming up here, right? We have 0.004 moles. And for hydroxide, it's 0.003 moles. Initially, we don't have any acetate, and then water is a liquid, so we can cross that out. We don't really care about it. All right, in order to find the change, if we're dealing with moles instead of molarity, you just subtract the smallest one. So between 0.004 and 0.003, 0.003 is smaller than 0.004, so you're going to subtract that one. So that's going to be our change overall. So minus 0.003 minus 0.003. And then on the other side, we're adding because it's a product, we're creating it, so we add 0.003. And so acetate at the end is going to be 0.003 moles. Hydroxide will cancel out 0, and then 0.004 minus 0.003 is 0.001. And so at the end of the reaction, we have acetic acid at 0.001 moles, 0 hydroxide, and then 0.003 moles of acetate. All right, and then for part C, it says for the reaction in part B, so what we just did, what is the limiting reactant, acetic acid or sodium hydroxide? And so for that one, it is going to be sodium hydroxide because it's the one that is completely used up. So if you are completely used up, you are the limiting reactant. We can't react anymore because you are completely used up. We don't have any more hydroxide left. So if you are 0 at the end, you are the limiting reactant. All right, and then for part D, it says to classify the reaction mixture in part B as either an acid, a base, or a buffer solution. And why does your answer in part B not reflect the actual final reaction mixture? All right, so for this one, I'm going to go ahead and scroll up just a little bit. There we go, I'll scroll like right there. So for this one, it is going to be considered a buffer solution. And the reason it is considered a buffer solution is because if you notice right here, I'm going to play around with these metallic colors. We have only acetic acid at the end, and we have acetate at the end. Nothing else is present at the end. So whenever you have acetic acid and acetate present at the end, then that's going to be a buffer solution. So this is not the final reaction mixture because the buffer solution needs to go all the way towards equilibrium. So it hasn't reached its final endpoint yet, but it is a buffer solution since it contains both acetic acid and acetate. So whenever it contains a weak acid plus its conjugate, that is going to be a buffer solution.